In this video, I'm going to cover section 7.3, general concept of point estimation, and 7.4. So let's start with from the unbiased estimator. So we want to figure out which point estimators are unbiased and then which one uh, is the biased, okay, estimator. So first, look at this. Give me a second. So now the point estimator of data head is an unbiased estimator for the parameter data if E, right? Expected value of data head, which means that the mean of the probability distribution of data head is equal to data, which is the population, the parameters. Okay. So, but probability distribution of data here, data head is statistic. Okay. I mean, point estimator. Sorry, point estimator. But normally, what the data head, I mean, statistic uh, is considered as the point estimator. So a probability distribution of data head can be called as a sampling distribution of data head because sampling distribution is probability distribution of the statistic. So now clear. So keep in mind this. So which I mean point estimator data head is a unbiased estimator. It means that what the mean of the probability distribution of the point estimator is equal to what population parameter data. Okay, so if the estimator is not unbiased, means the bias, that means what the E of data head minus data, which is the difference between the mean of the probability distribution of data head and the population parameter, is the has the such as non value. Has a non-value. Okay, so that is called the bias of the estimator there. Let's see example 7.3. Okay, so give me a second. All right, so example 7.3. Okay, so see. Okay. All right, so suppose that, excuse me, x is a random variable with a mean mu and variance sigma square. Let x1 through xn be a random sample of size n. I told you in a sample, it's a sample data. X1 through xn are what random variables. Okay, so they are called a random sample. Okay, so I mean that sample is called random sample. Can be a random sample of size n from the population represented by x. So show that the sample mean x bar and the sample variance s square are unbiased estimator of mu and sigma square respectively. So yeah, so let's prove it. Okay, so here we want to prove that what sample mean and sample variance are unbiased estimator. Okay, so that means what the you can see that. So give me a second. Oh yeah. So that means right there. So you can say that means what expected value. I mean the mean of the probability distribution of data head minus data is equal to 0. Right? Okay. So then we say that the point estimator, sample mean, and then sample variance are what unbiased estimator. Okay. Mm, so we're gonna use this one. X bar is equal to sum all of the sample data divided by number of the sample size. Okay, in section 5.6. Okay, so now the you see and then let's say E of xi is equal to mu, So I told you what the xi. It told you each sample data can be considered as a random variable, right? So in 5.6 we learned this. The what? This is actually what the 1 over p sigma xi over p can be considered can be rewritten as the constant 1 over p times the linear combination of xi, right? Okay, but in 5.6 we learned that what the expected value of linear combination of the expected value is the what the this is equal to what then, and then e of the expected value of each xi is mu, then this is expected value of x bar is equal to mu. So is right here. So e of x bar is equal to, okay, so sigma p I equals 1 and then xi, okay, divided by p, right? And then expected value of x bar, okay, that is equal to 1 over p, okay, times sigma I equals 1 through the p and the expected value of xi. Okay, can say that the e of xi, if e of xi is mu, okay, by the way x bar is a sample mean, okay, so if you say this is mu, okay, then this is equal to 1 over p times what, p times mu, so which is mu. I proved this, okay, so if you don't remember this one, just go back to 5.6, okay. So thus the sample mean x bar is unbiased estimate. You see, sample mean. So considering this one as a theta hat, get theta hat, then x bar. This is what expected value of theta hat is. That was turns out to be what, mu. So we can say that what the sample mean x bar is what unbiased estimator of the population mean mu. Okay. What about sample variance? So sample variance is e of s squared. Okay, we're gonna start from this and then doing this and what we have to get what the sigma square. Right? So we're gonna consider the s square as the what the point estimator of population variance sigma square. Okay, so now then this is equal to expected value of s square is what sigma I equals 1 to the n and then xi minus x bar, not mu, sorry, x bar square, okay, divided by n minus 1. Okay. So now this is equal to 1 over n minus 1, because this is 1 over denominator, I bring out of the expected value. So we got the expected value of sigma I equals 1 through the n, and then xi minus x bar square. Okay. So you may confuse that why I use the p right here and why I use n. Okay, it doesn't matter. Okay, you can use n instead of p here, or you can use p instead of n. It doesn't matter. So in here, I just set the sample size p. Okay, here I set the sample size n. So now the next one, yeah. So we're gonna FOIL. Okay, so that perfect square form. So that is equal to 1 over n minus 1 times expected value of sigma I equals 1 through the n, the xi squared minus 2 x bar xi plus x bar squared. Okay. So now then, this one, what? C, wait a second, 1 over n minus 1 times expected value. You see that I'm gonna apply the sigma for each term. Then we get this sigma I equals 1 through the n and an xi squared. Okay, the minus 2x bar and the sigma I equals 1 through the n xi. and the plus, and the what sigma x bar square is what? N times x bar, isn't it? X bar square. And then this one is equal to what? N times x bar. Okay, because what x bar is equal to sigma xi and I goes 1, okay, divided by n, right? So it means that what? N times x bar is equal to sigma I goes 1 through the n xi, right? Okay, because of this. So now then what? Now this is equal to, then here we got this negative 2 times n times x bar square plus n times x bar square. So we can combine the last two terms. So we got this 1 over n minus 1 times expected value of sigma I goes 1 through the n xi square, the minus n times x bar square. Okay. So now then, give me a second. So now this is what? Just what is this is just a linear combination of xi square and n times x bar, right? So we're gonna apply. I mean that one is equal to. By the way, this is equal to what? 1 over n minus 1 times sigma I goes 1 through the n and the expected value of xi square minus n times expected value of x bar square. Okay. So now then that is equal to, so you see that e of xi squared, that's going to be what? By the way, see right here, that is equal to 1 over n minus 1 sigma I goes 1 through the n, and then mu square plus sigma square, and then minus n times mu square plus sigma square over n, because this. How come? Why we got this mu square plus sigma square for the e of xi squared? Because this the sigma square is equal to v of xi. Okay, that is equal to expected value of xi square minus expected value of xi square. Okay, so down then what? So e of xi is what? This is mu, right? Okay, so we got mu squared, so that is equal to mu squared. Okay, so you see the equation. You see, this one right here. You see, sigma square is equal to e of xi square minus mu square. So from here, we got this. E of xi square is equal to mu square plus sigma square. Okay. So now, that's the first one. The second one is this. V of x bar, that is equal to E of x bar squared minus E of x bar, oops, square. Okay. But E of x bar is what? Mu, right? We prove it. So that is equal to sigma square. So sigma square, that is mu express sigma square over, in this case, n, right? Okay, n. Okay. So now then, let's see. Let's see. N. second. So if you don't understand what I'm doing, so please go back to section 5.6, linear functions of random variable. Okay. So when I covered this one, I told you this is really important. Um, I told you so because we're gonna use a lot in chapter 7. So I told you. So here, what I use this one, the variance of linear functions and the mean of linear function too. Okay, and then you see mean and variance of an average. So I use this one. You see the V of X bar. What's X bar? X bar is a sample mean. Okay, summation of the sample data divided by the sample size. Okay. So here P is a sample size, x1 through xp are sample data, but in statistic, these are random variable, okay? So the variance of the x bar is equal to sigma square over P, we see that right there. And then expected value of sample mean is mu. So the why the variance of x bar is equal to sigma square over P, because you see that right there. The variance of linear function, look at this. Yeah, so give me a second. So let's say y is a linear combination of the random variables x1 through xp. Then variance of the y is equal to c1 squared times v of x1 plus up to cp squared times v of xp. You see that? Because of this, I'll show you. If you still don't get it, let me give me a second. Let me show you. So why this v of x bar is equal to sigma squared n? Because so v of x bar is what, sigma, right? Sigma and the xi, I equals 1 through the n, okay, divided by n, right? Okay, I know in the section 5.6 they use a p, letter p as a sample size, but let me use the letter n. Okay, here we use a letter n for the sample size. So that is equal to then v of okay, 1 over n times x1 plus 1 over n times x2 plus 1 over n times xn, right? And then well, since this is a linear combination, right, of the xi, this is equal to 1 over n squared as v of x1 plus 1 over n squared v of x2. Right? Okay. So now let me see, and this plus. Let me see. I need more space. So that is. Let me write it again. Okay. So v of x bar that is equal to 1 over n square v of x1 plus 1 over n square v of x2, 1 over n square v of x3, okay, plus 1 over n square v of xn, okay, right. So this is equal to 1 over n square. What about v of x1, v of x2, I mean v of xi? So what? The v of x1 is nothing but sigma square, okay, because x1 is a random variable. So give me a second. Oh yeah, okay. So then this is equal to sigma I equals 1 to the n and the v of xi, okay, So that is equal to, well, this is equal to 1 over n squared times n times sigma squared, which is what, sigma squared over n. Okay, I prove it. Now then, so now back to here. That's why v of x bar is equal to sigma squared of n. And then using the, uh, the fundamental definition of the variance is what? The expected value of the what? The random variable square minus expected value of the expected value of random variable square. Okay. But expected value of vx bar is mu. Okay. So now see, I prove it. Right? Expected value of x bar is what? Mu. I prove it. So now we got this. From here, we're gonna get this. V of x bar is equal to expected value of x bar square minus expected value of x bar square is equal to sigma square of n. And then this is equal to what? Mu squared, right? So let's see. So give me a second. Okay. So back to the here. So e of x bar square, that is equal to mu squared plus sigma squared over n. Okay. Okay. So now, give me a second. Now we go back to this like my lecture room right here. Okay, so now I prove that e of xi squared is what? Mu squared plus sigma square. I proved that what e of xi squared is what? Is equal to mu squared over sigma square. Mu squared plus sigma square, and then e of x bar squared is equal to what? Mu squared plus sigma squared over n. I prove it. Okay, so I prove it. Now and then, so we got this one. Okay. Now what? So mu squared. I mean here. So sigma and the mu squared plus sigma squared is equal to what? That's gonna be, you see, n times mu squared plus n times sigma square, and then negative n times mu squared plus sigma square over n is equal to this. Okay, simplify this algebraic expression. I mean, simplify this algebra, we're gonna get sigma square. Okay, so starting from the what v of x bar, we end up with what? It end up with the sigma square. So the sample variance must be what? Unbiased estimator, unbiased point estimator of the population variance sigma square. I prove it. Okay. So now next one. Yeah, sample variance square is an unbiased estimator of the population variance sigma square. I prove it. So you see, S is a bias, by the way, but here's a weird thing. The Yeah, S square is an unbiased estimator, but standard deviation S is a biased estimator. Keep in mind this. Okay. So, but for large samples, bias is very small. Okay, what's a bias? Bias is the difference between the point as expected value of point estimator and the population parameter. Okay, so there is not unique unbiased estimator. Yeah, so it could have the multiple unbiased estimator. Okay, so now same point 3.2. So variance of point estimator. So minimum variance unbiased estimator. But yeah, so we want to find out uh, we want to figure out the what smallest the variance of point estimator, right? So let's see, minimum variance unbiased estimator. If we consider all unbiased estimators of data, the one with the smallest variance is called the minimum variance unbiased estimator. That's called MVUE. Okay, MVUE. So yeah, I told you, see that there is not a unique unbiased estimator. Then definitely we want to find out the best unbiased point estimator, right? It means that the point estimator, we want to find the point estimator, I mean unbiased point estimator, which has the smallest variance. Okay, but that doesn't mean I'll talk about this one later. So think about this graph. So this one, this graph is the distribution of theta 1 hat. Let's say that. Okay, the other one is distribution theta 2 hat. So definitely what distribution theta 2 hat has the I mean distribution theta 1 hat has the smaller variance than distribution of theta 2 hat, right? So then, so you see, it has been possible to develop a methodology to identify MVUE in many practical situations, but that's beyond of this course. But yeah, so when we do not know whether MVUE exists, we could still use a minimum variance principle to choose among competing estimators. So this is, for example, so let's think about two possible estimators for for mu, okay, x1 x bar, okay, x bar and xi. So yeah, x bar is what sample mean, xi is sample data, okay. But we saw that what the expected value x bar is a mu, right? Also, expected value xi is also a mu. So which one is better than the other one? Which one is the a better point estimator? Then we find out the variance of x bar and the variance of xi. Okay. So the variance of xi, we proved that what variance of xi is equal to sigma square, and the variance of x bar is sigma square over n. And now definitely sigma square over n must be less value, has a less value than sigma square. Okay, so x bar, which is sample mean, must be better point estimator, and also this is unbiased estimator, right? So x bar is must be better unbiased point estimator than xi. Okay, so now next one, 7.3.3, standard error reporting a point estimate. So uh, here's a question: how can you measure the precision of the point estimator? Yeah, so point estimator is nothing but approximation of the population parameter. That we want to figure out how, we want to measure how close the point estimator to the population parameter. So we're gonna use standard error of the estimator. The following error has been used. Okay, so standard error is sigma theta hat that is equal to square root of variance of theta hat. Okay, this is nothing but standard deviation, right? So standard error means actually standard deviation. Okay, so we find the standard deviation of the point estimator. Okay, that's going to be measure of the precision of the point estimator. The second way is this: estimating the standard error. What if we do not know? Which there's no way it's hard to figure out the standard error. Then we wanna approximate the standard error. Okay, so it's called this sigma hat theta hat, okay, or s theta hat or se theta hat. Okay, excuse me. So here's an example. Suppose we are sampling from a normal distribution with a mu and sigma square. Then by the CLT, the distribution of x bar is normal with mu and sigma square of n. So sigma theta hat of x bar is equal to sigma x bar, that is equal to sigma over square root of n. This makes sense, right? Okay. So by CLT. Okay. So now, if we do not know sigma, but substitute the sample standard deviation as, okay, the standard error of the theta hat going to be sigma x bar hat, right? That's another denotation of the SC of S theta hat. That's going to be S over square root of n. Okay. So you see by CLT, yeah, so by CLT, the distribution of x bar is normal with a mu and sigma squared n. But I told you, normally in a population, usually population parameters are unknown. Okay, because we don't know population. We don't know the all the set data in population. So normally we don't know sigma square. What if we don't know sigma square? Then we're gonna replace this one by the sample standard deviation s. Okay, so now we replace sigma s squared by s. That's gonna be the what standard estimated standard error. Okay, see. Yeah. So see 7.4 is thermal conductivity. So this is simple. Okay, so I'm gonna skip it, but please read the example okay in the textbook by yourself. Okay, and the 7.3.4. Let me cover this one from the next video. Okay, so let me stop here. So I'm gonna start from 7.3.4 next time.